Alright, in this video we look at more complicated spherical coordinates problems, just like we did in the polar coordinates problems, where maybe our our limits of integration were functions of the new coordinate system. So this is what we're seeing or being asked to do in this problem, is to look at a particular integral that's been given to you in rectangular coordinates, and then we want to write this as an integral in spherical coordinates. So that's what we need to do. Okay, to get started on this problem, I have taken the liberties of copying the problem over into Mathematica. You can see here I've evaluated the integral, and what you're not seeing here is how long this integral took the computer to evaluate. It took it about a good minute to evaluate this integral to pi. Okay. I have done what we've done in lots of previous videos. I have used the region plot command to plot the sphere that's involved in this problem. You can see that we're going on the bottom in this integral from z is equal to 4. That is the equation of this plane that you're seeing here, z equals 4, up to z is equal to the positive square root of 25 minus x squared minus y squared, which is essentially code for x squared plus y squared plus z squared is equal to 25, which is the blue top half of the sphere. Okay, but what we're seeing in the rest of the limits of integration here is that y and x are restricting this region of integration from the whole sphere to only a portion of it, which is the top part of this sphere. This is called a spherical cap. It is just finding the volume or the mass of this region in orange, whose density function varies with x squared plus y squared plus z squared to the negative 1/2 power. And the mass of this region is evidently pi, according to that Mathematica calculation. So what we need to do is to switch this to spherical coordinates, this integral. We can double check our answer in spherical coordinates, and we need to set up the limits of integration in this problem. Okay, so in spherical coordinates, there's some things that we can accomplish pretty quickly. Okay, we can go ahead and convert the function over to spherical coordinates. X squared plus y squared plus z squared is equal to rho squared. Okay, and then we're going to come up with our compensation factor, rho squared sine of phi, d rho, d theta, d phi. So there is dv in spherical coordinates. Here is our function f, our density function in spherical coordinates. And all that remains for us to do is to do the hard part now. Come up with the 6 limits of integration. Okay, like we did in the polar coordinates videos, we essentially, let me see if I can sketch this problem real quick. We have the top half of the sphere. Okay, I'm just sketching the region was shown to us over on the left. We had the plane z is equal to 4, and the region that we're trying to integrate over is this orange region here. Okay, now what we're essentially finding is that this region is made up of spheres, or top parts of spheres, of increasing radii. Okay, so we can imagine spheres getting filled out here. Okay, but every point in this orange region, every point that's in that region is on a sphere of some radius. Okay, so what we're imagining here is that any point in here is on a sphere of some radius. Even the points that are on the bottom plane are on a sphere of some radius. What we don't know is these spheres are centered at 0, 0. Here is the spheres coming out. And so we need to figure out what is rho. Rho goes from the bottom part of the plane to the top part of the sphere. Okay, so what we need to do is to describe there's a bottom and a top region. Okay, the bottom region is the plane. Z is equal to 4. Okay, there is a top region, and that is the sphere of radius, 5. That is the blue region. Okay. So what we're seeing is that we know that the top region of integration in terms of spheres is spheres of radius going up to 5. All of these points on the sphere are radius 5. Okay, but what we don't know is the bottom region, this plane, z is equal to 4. So if we look at z is equal to 4 if we look at z equals 4 in spherical coordinates, we know that from spherical coordinates, z is equal to rho cosine of phi. Okay, and so if z is also equal to 4, we can put these two ideas together to get 4 is equal to rho cosine of phi, and rho is equal to 4 over cosine of phi, otherwise known as 4 secant of phi. So this bottom plane here, depending on the angle down from the top, depending on the angle phi, the radius depends on that angle phi. Okay, and what we are seeing here is then that rho needs to go from 4 secant of phi up to rho is equal to 5. Okay, now we just need to figure out what the theta and the phi variables are. Theta is probably pretty straightforward because once you come down at some angle phi, right, and you let this angle theta swing around, you'll get all the points on a circle, right, at that angle of phi. So to get everything in this region, theta needs to go from 0 to 2 pi. What we don't know is how far of an angle to come down from the top. Here is phi is equal to 0. We need to figure out how far to come down here because we have to exclude this region outside of the orange region. So phi can't go to pi over 2 because that would come down here into this region. This is phi is equal to pi over 2. And we need to exclude this region. So we need to go definitely from phi is equal to 0 up to some value of phi that we still need to figure out. Okay, and let's see how we're going to figure that out. Give me just one moment to think and then I will come back. Alright, so here I've had a little bit of a moment to think. Let's take a look at what I've kind of come up with. So, like in the polar coordinates problems, we need to try to focus on a triangle. Do we see a triangle so that we can figure out what this angle phi is going to be at this maximum extent right here? So we're noticing that we have this top part of this height of the triangle. That is the height of the sphere 5. Okay, and this angle phi is measured from the positive z-axis. So here's the angle phi. Okay, and when that comes in and that sphere intersects the plane z is equal to 4, okay, let's see, that's plane z equals 4 is right here. So this is, instead of a height of 5 up to here, we have a z plane of 4. Okay, so this triangle right here has a height of 4. Okay, and let me see, we don't know this side of the triangle. I don't know what that radius is. Okay, but I do know that this side of the triangle will be equal to 4 because that is a point on the sphere. I'm sorry, on the sphere of radius 5. So that will be equal to a 5 here. Okay. So now we have two sides of a triangle and we have an angle phi. So we have a 4, we have a 5, and we have the angle phi. Okay. And so we know two sides of the triangle. Right. Here's our right angle. So this is the hypotenuse, and this is one leg of the triangle. So we can see here that the cosine of phi is equal to 4 divided by 5. So this is phi is equal to the inverse cosine of 4 divided by 5. And that is what our top limit of the integration is going to be. It is going to be the inverse cosine of 4 divided by 5. Okay. So now we need to see kind of how we did this problem. There's a lot of problem solving that went into it. And let's see if we have accomplished what we needed to do. I'm going to bring in the writing assistant, the palette writing assistant. We're going to go ahead and put in our triple integral for the volume of that spherical cap. And then we'll see, shoot, why won't that highlight? There we go. And let's go here again to put in another integral. And we can see that the function we're going to integrate is rho squared divided by rho. So we'll just go ahead and put rho times the sine of the angle phi. Okay. That is our function that we need to integrate. Sorry, this is rho. Okay, there's our function. Yeah. Typing here is a problem for me today. Let's see. And we want to integrate rho phi is our order of integration. And then we want tab to go to theta. All right, so there's our function that was pretty straightforward to come up with. We did that very early in the problem. And now we wanted to integrate from rho is equal to 4 times the secant of phi. That is the bottom plane. Z equals 4 bottom plane as a function of the angle phi. And then the top sphere is equal to 5. And let's see, this is the theta integral. Theta goes from 0 to 2 pi. And let's see, phi, we decided went from 0 to the inverse cosine, arc cosine of 4 divided by 5. And let's see how we did with this integral. Let's see if this evaluates. Comes out to be equal to pi, which is what the original integral was also equal to. All right. Now, evidently, this integral is going to be much easier to compute, even by hand. This integral evaluated, and you saw how quickly it was in about 2 seconds at the most. This integral really took the computer even about a minute to evaluate. So here is the volume of a spherical cap and how that integral is set up in spherical coordinates. And this is what we call a more complicated integral because the limits of integration are not all constant. Sometimes you have functions in your limits of integration.